Hi, my name is Dakota Archer, and I'm going to give an overview on action potential. So here I drew a neuron. Here is the dendrites, which will receive impulses and transmit them to the soma, or the cell body, which will then carry the impulses down the axon to the axon terminal, which will then transmit for further communication with other neurons. So anytime a neuron or a nerve sends an electrochemical signal, it is via action potential. Simply put, ions moving into or out of a neuron is an action potential. So at the resting membrane potential, here I drew a neuron without the dendrites or axon terminal. So here's the soma, and here's the axon. All right. So resting membrane potential, there is a chemical gradient where there's positively charged sodium ions that sit predominantly on the outside of the neuron. And then on the inside, there is positively charged potassium ions that predominantly sit inside. So this would be classified as polarized. So with our excitable tissues, there is a charge difference inside to outside. So this difference would be predominantly more negative on the inside of the neuron than on the outside. So at the resting membrane potential, we will see right around a negative 70 millivolts on the inside. So this, because there's a charged and a chemical difference, the neuron can be stimulated to send a signal. So to create the stimulation required, neurotransmitters must be released from a neuron. An excitatory neurotransmitter such as glutamate will then bind to glutamate receptors here. By traveling along the axon of another neuron, and the electrical charge that's created causes synaptic vesicles to carry these neurotransmitters across the synapse to this next nerve cell, which is here, where it will then bind to receptors. This binding opens receptors. So once glutamate binds to glutamate receptors, the binding will then open these channels for positively charged sodium ions to diffuse into the soma. Now, once enough positively charged ions diffuse into the soma, this will then bring the charge from a negative 70 up to a threshold of negative 55 millivolts, which will then, once this part of the axon is introduced to the threshold, will then open these voltage-gated sodium channels and allow the diffusion of positively charged sodium into this part of the axon, which will then increase the voltage within. Now, as this threshold moves down, it creates a domino-like effect where these channels, voltage-gated sodium channels, will continue opening as the threshold is met down the axon, allowing the diffusion of more positively charged sodium. Now, what happens is, as we move down, if I can find my cursor, bear with me. As we move down the axon, the internal charge continues rising, bringing it right around to a positive 30 millivolts. Now, once positive 30 millivolts is met, these voltage-gated sodium channels begin to close. Trapping positively charged sodium within. Now, simultaneously, what's happening is voltage-gated potassium channels also open once it hits around a positive 30 millivolts interior, which allows the diffusion of positively charged potassium to leave through the membrane, which will then cause repolarization, dropping the voltage inside. Now what happens is so much leaves so fast, it goes into a state of hyperpolarization, which drops below the resting membrane potential to around a negative 90 millivolts. Now this will happen all the way down the axon to the axon terminal. Now, hypopolarization is crucial to a healthy neuron because it will keep it from being stimulated to send impulses too quickly. Now, to reset back to a resting membrane potential, what happens is we have sodium potassium pumps right embedded in the membrane that will pump out 3 sodium ions out and then pull in 2 potassium ions, which will in turn reset it back to its chemical electrical gradient. And that was action potentials. Thank you.